Hello everyone, this video is about torque and static equilibrium. So let's go through the torque formula and understand the two basic conditions for static equilibrium. Stay tuned until the end because we're going to solve an example problem. Alright, so what is torque? Well, torque is a measure of the effectiveness of a force in changing or accelerating a rotation. In other words, is that force that when applied to an object changes its angular velocity. So that's the formula we use to calculate the torque, okay? So it's R, which is the distance from the pivot point to the point where the force is applied, times F, that's the magnitude of the force, times sine of theta. Theta is the angle between the force and the vector directed from the point of application to the pivot point. So let's understand it better using this example here. We have a beam that's attached to a wall at point A, okay? So then we exert a force right here. This force is at a certain distance from the pivot point, okay, R, and also it has a certain angle here, okay, between the force vector directed from the point of application to the pivot point. So because we have this force here, this beam tends to turn, okay, and this force here that's turning the beam is actually torque, the torque. But if you take a look here, the only component of this force that's making this turn here is the y component of the force. That's this force here that's pointing down, okay? Because the other part of the force that's pointing in, okay, that's pointing to a point, it's actually not rotating the beam, only the force that's pointing down here, okay, that's perpendicular to the beam. And that's how we calculate torque. Very good. Now let's go through the conditions for static equilibrium. Well, we have two conditions basically, okay? We have that the net external force on the system must be zero, okay? That's derivated from Newton's laws. So we have that the net force is zero for static equilibrium. So the sum of all the forces acting the x direction must be zero. The same thing for the y direction, okay? Everything that's pointing up must be equal to everything that points down in order for this to be zero, okay? Well, the second condition for static equilibrium has to do with torque. And it says that next to the net external torque on a system must be zero. Okay, so it means that all the torque that's acting in an object, making it turns clockwise, plus all those forces that acting on an object, and it makes it turns anti-clockwise. If we sum all these torques here, it must be zero. Okay, so everything that's turning clockwise plus everything that's turning anti-clockwise is zero. If we have these two conditions here, we have static equilibrium. So stay tuned now because we're going to solve a practical example that will make things much clearer. Okay, so here's our example. We have the same beam pinned to point A, okay? But now we have the distance R is 3 meters, our angle is 60 degrees, and the force applied is 100 newtons. We want to find the resultant force and torque on A for static equilibrium. In other words, we want to find the reactions on A in order for this beam to be in a static equilibrium or not moving, okay? So, okay, let's start with the forces. We have that the net force in the x direction is zero and the same for the y direction, okay? So for the FAX, we have that this force is equals the component in the x direction. So it's F cosine of 60. So it's 100 times cosine of 60 degrees. That's 50 newtons to the right. Okay, this component here of the force is pointing to the left. So the reaction must be pointing to the right. Okay, the same thing for the y direction. Now it's F sine of 60 degrees, which is 100 times 6 sine of 60, and that's 86.6 newtons pointing up. Because this component here of the force is pointing down, the reaction must be pointing up. We have both components here. You can calculate the resultant vector, right? That's 100 newtons. And if you calculate the angle, we can calculate use the 86.6, the two components, okay? The tangent of the angle, it's one component divided by the other, which is 60 degrees also. So that's exactly a force pointing in this direction. See that we have only one force here acting on this beam. So obviously the reaction must be the exact same force but pointing the opposite direction. And that's exactly what we calculated here, right? And now for torque, well, this force here pointing down, it tends to make the beam turn into the clockwise direction, right? So you have that the torque is Rf sine of the angle 60 here, okay? Which is 3 times 100 times sine of 60. And this gives us a torque on A of 259.8 newtons meters. Well, this force here is making the beam turn in the clockwise direction, so our reaction must be in the anti-clockwise direction due to this resultant force here. Okay, so that's it. Hope you enjoyed and see you next time.
Now that you've learned the theory, it's time to put that to practice. Check out our next videos for practical problems.